All right. Hello, Dr. Bauer again, looking at section 2.4, sequences and series. I know that last video was quite long. I'll try to make it a little bit shorter this time, but we need all the detail to really understand how these things work. All right, so sequences in mathematics are ordered listings of elements. Elements could be anything, numbers or other non-number elements. But anyway, most of the time we'll be looking at elements such as, here's a sequence, 1, 4, 9, 16, 25, etc. And you probably recognize those as the perfect square numbers. But sequences are used in many areas of discrete math and in many computer applications. Sequences can be defined by a list, like the list I just mentioned, by a rule, like perfect squares. This could be denoted by the list perfect squares. That's a rule. Or a function, such as, and then we have this notation where we have a set of braces with a sub n. Now, a sub n means the nth term. So, in other words, we're going to have a formula for the nth term, but we're saying that if you have a set made up of nth terms where the nth term is equal to n squared, for n equaling 1, 2, 3, etc. All right. So it gives you a little, this gives you a function to indicate what the term is depending on n. Okay, we call that an explicit formula where a sub n, the term, a1, a2, a3, a4, for whatever value of n you want, is equal to whatever n is squared. All right. And so that would define this same set of perfect squares. The definition of a sequence is that it's a function from a subset of the integers, usually either 0, 1, 2, 3, etc., or 1, 2, 3, etc. So it's from that domain. The domain is the set of a subset of the integers to a set S. Now the set S is the terms in the sequence. All right. So it goes from, the n's, which are the integers, a subset of the integers, to a set S, which are some values in the sequence, but we don't know what they are depending on the formula. So we denote the image of integer n as a sub n. So you notice we're going from n and then arriving at a term, a sub n. A sub n is the nth term, okay? A sub n should mean to you the nth term of some sequence, okay? And the sequence, we say the sequence of a sub n, all right? So in the example, list the first four terms, which would be a1, a2, a3, a4, of the sequence a sub n, where a sub n equals 3 over 2n plus 1. All right, so we have a little formula for figuring out what any term is. All we got to do is plug in the n. All right, so we plug in the numbers 1, 2, 3, and 4, one at a time, into the formula. And so if I plug 1 into the formula, I get 3 over 2 times 1 plus 1, or in other words, 3 over 3. So you get 3 over 3, which is 1. So the first term is 1. That won't always be the case, but this time it was. Now when I plug in when I plug in 2 for n, then a2 would be 3 over 2 times 2 plus 1, which is 5. So 3 over 5. So the second term is 3 over 5. When I plug in 3, okay, 3 over 2 times 3 plus 1, which would be 3 over 7. So the next term is 3 over 7. Next term after that, A4, I plug in 4, so 3 over 2 times 4 plus 1, which is 9, so 3 over 9, which reduces to 1/3. So always reduce fractions if you can. In most cases, we'll do that. So then the sequence is 1 3/5, 3 over 7, 1/3, which is the same as 3 over 9. But these are the first 4 terms of the sequence. Okay. So let's talk about one type of sequence called the geometric progression. A geometric progression is a sequence of the form a times r, a times r squared, a times r to the third, all the way to a times r to whatever power of n you want to put in there. Okay? So what are we doing here? Well, we're multiplying the previous term times r. So you have a starting term a, so that's the initial term a, and then you have what's called the common ratio r, but basically the common ratio r is what you're multiplying any term by to get the next term. Or another way to think of it is I could take any term and divide it by the previous term and get r. So like if I took AR and I divided it by A. Well, of course, the A's would cancel, so you just have R over 1 or R, the common ratio. If I used AR to the second power over AR, well, the A's would cancel and one of the R's would cancel. You'd still get R over 1 or R. So you'll find that if you take any term of the sequence and divide it by the previous term, it'll give this same common ratio R. So that's another way we can define what R is, the common ratio by taking any term and divide it by the previous term. Or you could think of it as any, or the number that we multiply by to get the next term in the sequence. Here's an example. List the first 4 terms of the sequence B sub n, where B sub n, or B of n, equals negative 2 to the nth power for the domain 0, 1, 2, 3, 4. Okay, so this time we're not starting at 1, we're starting at 0 for n, and so we plug in 0 for n, so B sub 0 is equal to negative 2 to the 0 power. Now anything to the 0 power is equal to 1. So the first term in this sequence is 1. The second term, if I plug in 1 for n, it would be negative 2 to the first power, which would be negative 2. Then if I plug in 2 into this, well, negative 2 to the second power, well, it'll be negative 2 times negative 2, which is positive 4. All right, because the negative squared is still a positive. And then B3, well, we're going to plug in 3 here, so negative 2 to the third power, which gives us negative 8. Now, you'll notice that the first term was 1. B0 is 1. So in terms of this A and R parameters, A is the first term or initial term, which is 1. And you'll notice that if we multiply by negative 2 every time, we get the next term. Because the first term was 1, the second term was negative 2, so we multiplied 1 times negative 2 and got negative 2. Multiply by negative 2 again, and we get positive 4. Multiply by negative 2 again, we get negative 8. So you'll notice that we're multiplying by negative 2 every time. Or you could use the note that if we divide any term by the previous term, you know, and I show several examples of doing that, negative 2 divided by 1, 4 divided by negative 2, negative 8 divided by 4, all of those ratios are equal to negative 2. Okay? Now, in the last example on the page, list the first four terms, D0, D1, D2, D3, for the sequence D sub n, where D sub n is 8 times 3 over 2 to the nth power. All right, so notice we're finding D0, so n is 0 first of all. And so I plug in 0 for n right here in the formula right here. So it'd be 8 times 3 over 2 to the 0 power. Now, of course, anything to the 0 power is 1. So the parentheses to the 0 power would be 1. So we have 8 times 1, which gives us 8. When I plug in 1 into the formula for n, we have 8 times 3 over 2 to the first power. And the 2's cancel, leaving 4 times 3, or 12. So the second term is 12. If I plug in 2 into this function, we have 3 over 2 squared, which would be 9 over 4. The 4's cancel, leaving the 2, so 2 times 9 gives you 18. You can work that out and see that if you're careful. So the next term is 18. And then you plug in 3 for n, and you get 27. So the terms of the sequence are 8, 12, 18, 27. And you see that the initial term is 8, so a is 8. The ratio of any two terms is 3 over 2. And you can see that by doing 12 divided by 8, that reduces to 3 over 2. Or 18 divided by 12, that reduces to 3 over 2. Or 27 divided by 18, that reduces to 3 over 2. So in each case, the ratio, the common ratio, is 3 over 2. And you can see that we're multiplying by an additional 3 over 2 every time. We're raising the power on the 3 over 2, so that in essence is multiplying by 3 over 2. Anyway, the first four terms are these listed. Oops, sorry. So arithmetic progressions. This is another kind of progression. Instead of geometric progression, sometimes sequences are arithmetic progressions, okay? And then there's some other progressions or sequences that are neither of those two things. But an arithmetic progression is a sequence which can be put in the form a plus d, a plus 2d, a plus 3d, a plus 4d, as many times as you want, all the way to a plus nd, where n is the number of the term. So actually we're going to start with n being 0 here, not 1, but anyway. So the initial term is a, as you see in the sequence, and the common difference this time, not the common ratio, but the common difference is d. And you can see that if you take any term and subtract the previous term. So arithmetic progressions are identified by whether subtracting any term from the previous term, or I should say subtracting the previous term from any term. I'm going to have to. Okay, so now instead of geometric progressions, now we're going to look at arithmetic progressions. This is another type of sequence that you could have. There are lots of types of sequences, but this is another type. And so the definition says that an arithmetic progression is a sequence which can be put in the form a plus d, a plus 2d, a plus 3d, all the way to whatever a plus n times d term you want to talk about. So a is the initial term, and d is what we call the common difference. Now, if you notice, if I took the term a plus d and I subtracted the previous term, if I subtract a from a plus d, I get d. Likewise, if I take a plus 2d and I subtract a plus 1d, the a's disappear and 2d minus 1d leaves 1d. Same thing with a plus 3d minus a plus 2d. You get 1d. So arithmetic progressions are identified by whether subtracting the previous term from a term gives a common difference d. So let's look at an example. Write the first 4 terms of the progression sequence C of n, where C of n equals -3 plus 5n, where n is 0, 1, 2, 3, etc. So we want to do the first 4 terms. So we start off and we plug in 0 into this. So C0, we're plugging it into this formula right here. C0 would equal -3 plus 5 times 0, or in other words, -3. So your initial term is -3. Then C1, if I plug in 1, it would be -3 plus 5 times 1. I'm just plugging 1 in for n. And that yields 2. So the second term is 2. Then the third term, if I plug in 2 for n, C of 2 would be -3 plus 5 times 2, or in other words, -3 plus 10, or 7. C3 would be -3 plus 5 times 3, which gives you 12. So the sequence, the first 4 terms of the sequence are -3, 2, 7, and 12. Now note that the first term is -3, and we're always adding 5 to get the next term. Or you could look at it this way: if you subtracted any term minus the previous term, so 2 minus -3. Well, 2 minus -3 would be 2 plus 3, or 5. 7 minus 2 is 5. 12 minus 7 is 5. So it should always be the case, if it's an arithmetic progression, that we can take any term minus the previous term and we'll get the same common difference. Okay. Now, recurrence relations are something we use in programming to do things that we couldn't do otherwise, and they relate to sequences such as the ones we've just looked at. A recurrence relation, also called a recursively defined sequence, is a sequence a sub n defined by an equation that expresses a sub n in terms of one or more previous terms of the sequence. That's different than what we've been doing. We've been doing defining a term by n, plugging n in. Here you can't do that. You can't plug in n. You have to know the previous terms of the sequence, and then you can figure out the next term. So that's what I'm saying here. It expresses a sub n in terms of one or more previous terms of the sequence, such as a0, the first term, or a sub n minus 1, the term just before the a sub n term, or a sub n minus 2, the term 2 before the a sub n term. So in addition, one or more starting terms, such as a sub 0 and a sub 1, must be exactly specified. So you got to have specified those starting terms, and then you can find the next one, and then the next one, and then the next one, on down the row. But let's say you wanted to find the 50th term. Well, you couldn't find the 50th term until you found the few before that, like the 48th term and the 49th term. So it's not one that you can just plug in n and figure out the term. You're going to have to go all the way through there. So that's why computer programs that can do loops and figure out these things are valuable or related to this. A sequence is a solution to the recurrence relation if its terms satisfy the recurrence relation. So there'll be some equation that we say is the recurrence relation that relates the terms, but a solution is going to be like a formula with n in it that we could find any term we wanted that satisfies that recurrence relation expression. So here's an example. Let a sub n be a sequence that satisfies the recurrence relation a sub n equals 2 times a sub n minus 1. Now notice, and then minus 5. But notice that a sub n is not defined in terms of n, but it's defined in terms of a sub n minus 1, which is the previous term. See, if a sub n is a particular term, when the subscript is 1 less, n minus 1, then it's the previous term of the sequence, okay? So what this says is, to get a term, take 2 times the previous term minus 5 and subtract 5. So go 2 times the previous term and subtract 5. All right? So let's look at these terms and figure out how to come up with the, as it says in the problem, what are A1, A2, A3, and A4. Now, another important piece of information here is a sub 0 equals 7. So that tells you where we start. What value is your first term of the sequence? That way you can get the next term of the sequence. If we didn't know that piece of information, we could not find the terms in this sequence. All right? So if A0 is 7, let's find A1, A2, A3, and A4. Now, from the equation, if for n equal 1, well, I'm putting in 1 here, so 1 minus 1 in the subscript becomes 0. Now, really what we have is not 0, but a sub 0. So what this reverts to is 2 times a sub 0 minus 5. Well, a sub 0 is the previous term. Looking at the first term, the previous term would be a sub 0. Okay, and so a sub 0, we know it's 7. So I plug in that. So 2 times 7 minus 5, 14 minus 5 gives you 9. All right. So then when n is 2, our subscript is 2 minus 1. So our subscript is always, 1 less on the right side of this equation. So a sub 2 minus 1, which is a sub 1. Now we know what a sub 1 is because we just found it. It's 9. So we got to go 2 times 9 minus 5, and that equals 13. So we're always using that previous term. And so you can see what we did. You don't have to look at this other stuff here. Just look at this column right here. We're taking 2 times the previous term minus 5. So 2 times the 13, which is the previous term, minus 5 gives us 21. 2 times the previous term, 21, minus 5 equals 37. So you see, this is the sequence of terms after your first number, 7. So 7, then 9, 13, 21, 37 is your sequence. Now, is this geometric? Could we take 7 and multiply by something to give us 9? And then the same number multiply by 9 and give us 13? No, we can't. So it's not geometric. Is it arithmetic? Well, if we take 7, what do we have to add to that? Because arithmetic is always adding to get the next term. What could we add to 7 to get 9? Well, we'd add 2, but can I add 2 again to get the next term? No. We add 4 this time. And then after that, we add 8. And then after that, we add 16. So we're not adding the same thing. Now, I know there's a pattern to what we're adding, but it has to be that we're adding the same thing to be arithmetic. Okay? So this is not either of those types. All right, so let's look at some more examples of recurrence relation. If b sub n is given by b sub n equals negative 3 times b sub n minus 2 plus b sub n minus 1 for n equals 2, 3, 4, etc., with b sub 0 being 2 and b sub 1 being 5, find b sub 2, b sub 3, and b sub 4. So here's what I did here. If n is 2, because we're starting off where n is 2, if n is 2, then b sub 2 would be negative 3 times 2 minus 2. Well, 2 minus, negative 3 times b sub 2 minus 2, which is 0, b sub 0. So negative 3 times b sub 0 plus b sub 2 minus 1. Well, 2 minus 1 is 1, so this is b sub 1. So the first thing I do is I plug in 2 and I figure out which terms I'm going to use here. In this case, I'd use b sub 0 and b sub 1. And then I'd look up what those are. Well, it gave me that b sub 0 was 2 and b sub 1 was 5. So I plugged those in. So it's negative 3 times b sub 0, which was 2. So negative 3 times 2 is negative 6. Then I add negative 6 plus b sub 1. b sub 1 is 5. So negative 6 plus 5 is negative 1. b sub 3, well, we plug in 3 into this, and so you get these subscripts, negative 3 times b sub 1 plus b sub 2. Well, b sub 1 was 5, and b sub 2 we just found was negative 1. So negative 3 times 5 is negative 15, plus negative 1 is negative 16. So this is very tricky if you're not really careful with what those subscripts are and what they mean and what b sub whatever it means, b sub 1 means, the first term when n is 1, and you got to go look up and find what that is in the problem. In this case, it's 5. Anyway, b sub 4, if you plug in 4 into this recurrence relation, it's negative 3 times b sub 2 plus b sub 3. And if you plug b sub 2 and b sub 3, the previous values that we just found in there, you get negative 13. So the terms of this sequence, at least the first several terms, well, the first one was 2, the second one was 5. They gave us those. Then negative 1, negative 16, negative 13. Now, obviously, this is not arithmetic. You're not adding the same thing to get the next term. And it's not geometric. You're not multiplying to get, so it's another one of these neither types. Now, the Fibonacci sequence is a special sequence defined by a recurrence relation. There's the initial conditions, f0 is 0, f1 is 1, all right? And this defines the recurrence relation. Now, what this is saying is to find the nth term, you take the n minus 1th term, in other words, the previous term, and add to that the n minus 2 term, or the term that's 2 before it. So so basically I'm just adding the 2 previous terms. So that's what I said. Essentially, you just add the previous 2 terms to get the next term. So what would be the sequence in this case? Well, let me get my writing tool. So the first terms are 0 and 1. We already know that from the given, 0 and 1. Now, the next term is going to be the sum of those terms. So 0 plus 1 is 1. So the next term is 1. So that's F2. Now F3, we take the previous 2 terms and add them. So I add 1 and 1, and that makes 2. Then I add the next 2, or the previous 2 terms to get the next term. So that one would be 3. All right, and then I continue to this process. I add the previous 2 terms, so 2 plus 3 makes 5. And then Add the two previous terms here. 3 plus 5 is 8. And then add the two previous terms. 5 plus 8 is 13. And then the two previous terms again, and I get 21, etc. So this pattern just keeps going on, and it grows and grows. Now there's a lot of applications to the Fibonacci sequence. Fibonacci sequence has been found to have a lot of places in mathematics that it's important. Okay, but you can look that up, and you'll see all kinds of applications to nature and all kinds of other things if you want to look at that. All right, so some more examples of recurrence relations. This one probably a little bit more difficult than the ones you'll have on a test or quiz, but write the first 5 terms of the recurrence relation a sub n, where a sub n equals n times a sub n minus 1. Now, if you haven't picked it up already, a sub n minus 1 is the previous term. But this recurrence relation is a little bit different because we're multiplying n times the previous term. So a sub 0 is 1. We start off with that. And then we're going to start plugging in 1 for n, and then 2 for n, 3 for n. So right here, we go a sub 1 would be, well, we go 1, which is the n term, times a sub n minus 1. So that's 1 minus 1, or 0. So 1 times a sub 0. Well, a sub 0 was 1, so it's 1 times 1, which is 1. Then the next term is we plug in, and we go n, which is 2 times a sub 1, because 2 minus 1 is 1. And a sub 1 was 1, so it's basically 2 times 1, or 2. The next term is 3 times a sub 2, which is 3 times 2, or 6. So we keep multiplying n times the previous term. So the fourth term will be 4 times 6, or 24, etc. So the terms are, starting with n equal 1, 1, 2, 6, 24. Now, we could write these as 1. Now, 2 is 1 times 2. 6 is 1 times 2 times 3. 24 is 1 times 2 times 3 times 4. So we could write this as just multiplying an additional number, and that essentially is the factorial function. F of n equals n factorial, which we just talked about a little while ago. Now, example 9 says, page 159, determine whether the sequence a sub n, where a sub n equals 3n, for every non-negative integer n, is a solution of the recurrence relation a sub n equals 2, a sub n minus 1, minus a sub n minus 2, for n equal to 2, 3, 4, etc. Now, they do give the initial conditions. A sub 0 is 0, a sub 1 is 3. So we know that a sub n is 3n. So what we can do is plug in a sub n, plug in n minus 1 for n to get the a sub n minus 1 term. So we plug in, instead of n, we plug in n minus 1, so it's 3 times n minus 1. And to get the n minus 2 term, the term with subscript n minus 2, we go 3 times that subscript, so 3 times n minus 2. So if we plug these things, a sub n minus 1 and a sub n minus 2, these formulas that we just found, into the recurrence relation up here, and then do the algebra. Let me move this down a little bit so you can see it a little bit better. 6n minus 6 minus 3n plus 6, which all simplifies to 3n. So that shows that a sub n is equal to 3n. So we just got a explicit formula for a sub n by, plugging it in there, and it does turn out to work. All right, if you end up with a sub n for the formula for a sub n, which is from the recurrence relation, then it verifies that that is a solution to the recurrence relation. So that's one way to that's a way to determine whether it's a solution to the recurrence relation. Now, how would you solve a recurrence relation if you didn't know what a solution was? Well, here's an example. Solve the sequence defined recursively as a sub n equals a sub n minus 1 plus 7 with a1 equal to 2 by finding an explicit formula, a formula where you can just plug in n to find any term. All right. So you might start looking at the terms. We know that a sub 1 is 2. Got that. So that's when n is 1. If I plug 2 in here, so a sub 2 minus 1, or in other words, a sub 1 plus 7, well, a sub 1 was 2 plus 7 gives us that expression 2 plus 7 for a sub 2. Now, don't add them together. Don't get 2 plus 7 or 9. Don't write 9, because what you want to find is a pattern for these terms. How did we find the terms? If you combine everything, you can't tell how you found those terms. All right, then a sub 3. Well, a sub 3 means take the previous term and add 7 to it. So the previous term was 2 plus 7. And you add 7 to it, so you get 2 plus 7 plus 7. And then in a sub 4, we take the previous term, which is 2 plus 7 plus 7, and add another 7. So what we're finding here is that you keep adding another 7, and so when n is 4, how many 7s do you have? You don't have 4 7s, you have 3 7s. When n is 3, you have 2 7s. When n is 2, you have 1 7. So you always have one fewer 7 than the value of n. So you no doubt notice that you have one less 7 than the value of n. Thus, we can write it as the number 2, because that's in everything, just plain old 2, plus 7 times 1 less than n minus 1. So that gives you a formula for that. Now, you could distribute the 7 and combine the negative 7 with the 2, and so you get 7n minus 5. So that's another way you could write that expression. But this process that we just did is called forward substitution. Now, forward because we're starting with 1 and going on upward, so it's in a forward direction. The previous slide was more of a backward substitution by plugging in formulas for the previous terms. All right, so here's another application problem. Suppose you earn 4% interest each year from an account. Thus, a sub n, where a sub n, thus it's the sequence a sub n, where a sub n is a sub n minus 1 plus 4% of a sub n minus 1. So what this is saying is that we're taking and saying that any term is the previous term plus 4% of the previous term. So wouldn't that add 4% interest every year to the previous value? So if I work and show this kind of a backwards way, starting from the nth term and working backwards rather than starting from 1 and moving on up, a sub n minus 1, okay, so you get this formula for a sub n, and then I take and, well, I can put that over here, and then I can replace the a sub n minus 1 with 1.04 times a sub n minus 2. and then I can replace that and 1.04 times a sub n minus 3. So you're always putting in the previous, you're substituting the value in parentheses in this case for the previous term, you know, and getting this formula. So 1.034 to the third power times a sub n minus 3. Now, if you carry this down and the subscripts gets lower, 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 then eventually you're going to reach a subscript of 0 for so be a sub 0. And then, of course, we know what a sub 0 is. It's the initial value of whatever was in the account. Okay, so the formula then, as it came from right here, 1.04 to the nth power times the initial value, or I rearranged it so that it starts with a sub 0, the initial value, times 1.04 to the nth power. So this is sort of a backwards substitution. So look at that and think about it. Look at also examples 12 through 16 to notice those patterns. Okay. So summations and summation notation. This is near the end. A useful construct in discrete math is what's called the summation, which is supported by summation notation. Now, this notation uses this Greek letter sigma, capital sigma, which looks like this. And this symbolism says that I, the index variable I, starts at 1 and goes up to 5. So starting with I equal to 1, then I would be equal to 2, and then I equal to 3, and I equal to 4, and I equal to 5. So what are we plugging I into? Well, we're plugging I into this formula 7i. So 7 times 1 plus 7 times 2 plus 7 times 3 plus 7 times 4 plus 7 times 5. Now, why are we adding these terms together? Because that sigma notation denotes a sum of all the terms of this expression. So whenever you see that sigma symbol, we're going to be adding the terms up in the sequence. So it's no longer just a sequence, it's a sum of a sequence. And if you multiply 7 times 1 plus 7 times 2 plus 7 times 3 and add those products all up, you get 105. Now notice the lower limit or limit variable for the index variable I is 1, and the upper limit is 5 for the index variable, called the index of the summation. Now, the upper limit can also be written above the summation symbol. So here's an example. This is saying I'm going to add up all the terms, n squared terms, where n starts with 1 and ends in 10. So that would be 1 squared added with 2 squared added with 3 squared all the way to 10 squared, which you get 385. Okay. Now in the next example, says we're going to take, it says that x bar equals 1 over n times the summation, and then I starts at 1 and goes to n of x sub I. So x1 plus x2 plus x3 plus x4 all the way to x sub n. And we add those up, and then we multiply by 1 over n. Has anyone seen that formula before? Well, that formula, because we add up all the terms and then we divide by n, which is the same as multiplying by 1 over n. What is it when you add up all the terms and then divide by n? It's the average. Exactly. This is the formula for the mean that you would see in statistics. Okay? But it's described in a summation notation. All right, next example. Note if you have summation from j equals 1 to 5 of j to the third power, well, that would be 1 to the third plus 2 to the third plus 3 to the third plus 4 to the third plus 5 to the third. But let's say you didn't want to make it start at 1. You wanted to make it start at 0 instead. How could you make it start at 0? Well, you could just add 1 to the value of the index, so that if you plugged in 0, 0 plus 1 would be 1. So really in the expression, it's starting at 1 in the parentheses. The parentheses would be equal to 1. So it's the same terms, 1 to the third plus 2 to the third plus 3 to the third plus 4 to the third plus 5 to the third. But your index variable is starting at 0 and ending at 4. Now when it ends at 4, I plug in 4 for k. 4 plus 1 is 5, so it's that last term. Example 21 in the text shows a double summation, sort of a summation inside of a summation. It's appropriate for what's called nested program loops, where you have a loop inside of another loop. All right, an outer loop and a smaller inner loop. But we can express this mathematically with a double summation. And then example 23 shows an application of such a formula. But that's the end of the section. Pretty detailed, so be careful again, and just work on it little bit by little bit. Spend a lot of time on it, looking at the details. All right, bye.